The title just shows the objective of my work, so you know already. This you know already. So the outline of my talk is listed up here. First, I show very briefly experimental methods, and then show the run tables we have done in 1.5 years. And thirdly, I show something new for you. This is strong gas turbulence effect by strong local anomalous heat effect in our experiment. This is a kind of new finding. And then I show some typical anomalous heat data. And fifthly, I show the circumstantial some evidences showing nuclear effect and concluding remarks. And some detailed data is given in appendix, very much in detail. So you will see this because I already uploaded this data in ResearchGate, so you can see anytime from there. So the experimental method is just we use, as you know, we have been using since several years the metal nanocomposite samples for doing anomalous heat effect experiments. And these samples are made by so-called melt span fabrication and then making a calcination to make nano islands in sample in somewhat ceramics, zirconia. And we made a repeated calcination that made a very good effect for enhancing excess heat power level. And by using the oil mass flow calorimetry system at Kobe University, and by using ordinary hydrogen or light hydrogen gas or deuterium enriched gas, and making calorimetry with some radiation detection, neutron and gamma ray mostly. And we start the experiment at room temperature to absorb hydrogen gas into sample, then elevate the temperature to show the anomalous heat effect coming out. And we repeat the experimental run after baking the sample and evacuation, and to repeat the absorption at room temperature and the elevated temperature to see the effect. And then we make taking out the sample from the reaction chamber and made a recalcination in electric oven and to repeat this similar experiment. And so step by step, we have seen the very significant enhancement of excess heat power. And I'll show some short one-day rise-up data of experiment and very weeks long-run data soon after. This is how to make a sample. I have shown several times in last conference, so just omit. Inside the ceramics, we will make a so-called nano island of nanocomposite sample, mostly nickel-based, but some minor metal like palladium or copper in our case. Okay, this is a Kobe oil mass flow calorimetry. And this is a calibration curve we have explained already several times, so just cut. This is a reaction chamber. Inside we have 4 RTD temperature sensors, and also the oil inlet outlet temperature is monitored by some couples. And on the upper flange center, we have some couple TC4. This will make a very interesting indication I'll show soon. This is after the first experiment using a copper 1 nickel 7 zirconia experiment using about 1 kilogram powder sample fully in the reaction chamber, and where we found a very big heat burst in 100 seconds, probably 3 kilowatt happened in our analysis. However, after disassembling the reaction chamber, we found the sample was expanded very much and stacked, become very hard. And also we inserted some ceramics gas guide that was almost broken, as seen in, around here. and also the upper flange has something deposit as Iwamura found. And this is the, this one is zirconia filler 1 millimeter diameter beads. And this is the CNG sample powder. This is a finer one, somewhat rough one, very fine. Size of about 0.1 millimeter is the usual size. And so I'll show some round tables, typical round tables for 3 samples. CNG is the, written here, copper 1, nickel 7, and zirconia sample. 1 kilogram we used for this run, CNG 7 runs, starting from room temperature. This is external heater power. We use a K3 constant power supply for this. So after room temperature gas absorption, starting with this gas pressure, and after the saturation of the absorption, we elevate the temperature, and we suddenly, after 1 hour or so, we found a big heat burst, 152 watt. Actually, this was about 3 kilowatt, 100 second heat burst we found later by analysis. However, after that, we cool it down again at room temperature and raise the temperature again and cool down and raise temperature again and repeat it, and showing the output excess power coming out. After this, power is not large, about 10 watt to less than 20 watt, something like that, for many, many days, about 6 months run. And this sharp one shows the first run, and sharp 2 means the after baking sample under evacuation, we made a similar experiment, starting from room temperature absorption, heating up, and again, and see the output excess power. Not very much enhanced this time. In average, about 40 watt excess power we observed in this. However, after making a second calcination of sample for this, we made a similar experiment for several months, and we observed the long-lasting excess power increased very much, 52 watt, around close to 60 or something. And after these runs, we made baking and evacuation again, and then observed the heat power increase about 30%, 70 watt. This is the maximum power I show you this time. However, after that we have some more, but I'll not show this time. And that CNG experiment is done with the ordinary hydrogen, so light hydrogen gas, so to say. However, this PNG10, this is the nickel with the palladium 1 to 10 in zirconia, you see here, and with deuterium gas, and the sample is 0.5 kilogram. So this is the palladium 1 nickel 10 zirconia sample, and we have done similar experiment with CNG type, and starting from room temperature raising up, and so on. This is the once we made a recalcination of sample. Before that, we have a PNG10 experiment that shows the excess power level very small, less than 10 watt. And by making a calcination, that increased to around 30 watt or so, roughly speaking. So, and then proceed more because time is limited. And we have seen the strong gas turbulence effect in this sample again and again, just show. This is a case of initial heat burst this one, and we have something very strange for the upper flange temperature, this, and oscillating this way, very strange. And we didn't understand why it happens, but later we found this is a kind of gas turbulence effect inside the reaction chamber. Because of the local strong excess heat, we have a strong stream of gas changing path of stream. That makes a big effect for calorimetry. We find so. And this similar thing happens again and again with other sample like CNG calcined sample. This is the upper flange temperature. This is rising up strongly and then become very flat, very strange. This is the oil outlet temperature. This is the reaction chamber inside temperature. This is a neutron signal, but I skip this. And so we did the trial experiment and changing the, the outer heater, external heater power changing from low power to high power and alternately changing. And what happens in power output. This is a case of power going down. Very strange, negative spike happens in outer flange temperature. And we found later this is a kind of gas turbulence effect inside the reaction chamber. Similar thing, so under this kind of effect, when we increase the heater power, the oil outlet temperature apparently decrease. This is very strange in contradiction. However, the average temperature inside the reaction chamber go very normally, reflecting this change. So we found the calorimetry by using the average RC temperature is very reliable. However, the oil outlet temperature might have sometimes problem because of this turbulence effect. So this is kind of finding. We have to be very careful. This kind of thing happens again and again, like this. When uppermost flange temperature go up very steeply, here we have kind of heat burst. And again, suddenly become very flat, very strange. However, because of this effect, the oil outlet temperature is also making this kind of, disturbance. Because the similar thing happens again and again. When inside temperature go up suddenly, this has a strong rise up temperature, burst-like, then making very flat. Maybe we guess a kind of gas upstream happened from lower part to upper part. This is a lower part temperature, so in reaction chamber. This is a kind of thunderstorm climate. We have similar thing happening, I guess. So kind of gas turbulence effect inside. Because of that, when we monitor the oil inlet outlet temperature, especially outlet temperature around here is disturbed by this turbulence effect cooling this upper flange. So measuring temperature significantly underestimation. And in that sense, this temperature monitor around TC1 is better to use than this point. However, still we have a disturbance. We have to be very, very careful to this. And from such knowledge, we understand now why we have this kind of fluctuation happened. We thought this is a kind of gas sorption and desorption oscillation, but it was not so. This is due to the gas turbulence effect. And finished here, because this is the average temperature in reaction chamber. Okay, this is 300 degrees. And this is the oil outlet temperature. this is very underestimated because of this we found. So this curve is more reliable. Because that for the heat burst, it's okay by using oil outer temperature because of we don't have such turbulence. After that, we have a gas turbulence. So this underestimates very much. This is more correct, more reliable to say about 40 watt excess remains. However, when we don't have a big heat excess power, three curves like upper flange temperature and oil outer temperature and average reaction chamber is very similar. This is a normal case we call, and very comparable to the calorimetry calculation run. In this kind of case, calorimetry by average temperature inside or oil outlet temperature is almost the same. So we have no problem in this kind of case. However, the power level is low, you see, about less than about 10 watt and so on. When power level becomes very high, we have problem. So the average temperature of reaction chamber is more reliable. We have run so. Then I want to show some typical heat power data. This is a case of CNG recalcined, the rising up curve, start experiment. We have a gas absorption, endothermic gas absorption in this case, and saturated here. After this, we have excess power coming out, going to about 50 watt. This is underestimation. And again, we repeat the experiment. You see, in this case, we have a dissolption gas. We have this kind of fluctuation. Does it have some good meaning? We don't know exactly. However, this might have some meaning, important, but we need analysis later on. However, this power coming out, about 50 watt. This is apparent power, but this is underestimation by oil outlet temperature. And this is the case, similar. And excess power happened under the after the gas dissolption and almost the equilibrium, small fluctuation, we have a continuous excess power coming out. This is a case of palladium nickel nanocomposite with deuterium gas. In this case, we observe this kind of heat hump at the beginning. This is a kind of small burst, then coming down. And so the heat power behave like this. This we have good agreement between two calorimetry. However, after this, you have a turbulence effect of gas, and so this is more reliable, about 15 watt. And after making, I think the baking, sample baking, power raised up to 30 watt, doubled. And we found now after this, we made the recalculation of this sample, and this power level, this power level raised up to 90 watt. Before we come in here, we found so, but such data I will not show this time, and I'll disclose such data in the coming Japanese meeting in December. So by making, the largest power we observed the 90 watt up now. However, from these results, we found the past experiment with PNG6RR and doubly recalcined one. We found inside very high local power, 50 watt. This was reliable, we found later. So, and in this case, we used a 120 gram sample. So this is corresponding to about 400 watt per kilogram. very high powers happened already. We find so. And so, and some circumstantial nuclear evidence, I don't have enough time, so just show neutron looks happening when the heat power going up. This is a neutron signal, very small, only 1 neutron per 10 joule or so, comparing to the about 1 neutron per 1 joule. We have a 13th orders magnitude smaller neutron yield we observed, very small. However, it looks happening. This is to just omit. And also specific reaction energy for long time operation, the value is very high, more than 100 electrons, sometimes over 1 keV, and difficult to explain by chemistry, of course. So this is some kind of circumstantial evidence of nuclear effect, we believe. And in the case of CMG sample, this value becomes much higher, over 10 keV or over 100 keV, and for about 27 days run, heat power is about over 60 watt. This kind of total power 128 megajoule in this case, or 27 days. So this is a case of palladium nickel with deuterium, similar value, but much smaller. But in this case, we have some gas leakage in the system, so maybe this specific reaction energy might be much higher, actual value. And some conclusion is very obvious, and still we have a little bit time. 1 minute, okay, so I can say some conclusion. Anyway, by anomalous heat effect is now very repeatable. And so we think the phenomena reproducibility is, we can say, established. Every time we can observe by using this kind of recipe if we use. And secondly, by using the palladium nickel or copper nickel binary and nanopowders, sustainable big level over 100 watt per kilogram level sustainable heat power is coming out. And this happens almost every time. And also in the beginning, the rise-up data, we have seen some interesting effect, and the gas turbulence effect and so on. And probably the condition to realize maximum heat power sustainable is making a dynamic gas, hydrogen or deuterium gas flux coming in and coming out through the surface, meaning desorption and absorption is competing on surface. That kind of condition is maybe less. We need to try to make experiment at higher temperature. We are now going to do this. And the other circumstantial nuclear evidence, which is weak signature of neutron correlating to power time dependence, and also the specific reaction energy per neutron transferred. We use this kind of measure. This is very high value compared to the chemical energy is less than 1 electron volt per hydrogen atom transfer, so far the very high value. And especially in the case of CNG, this is very high. So this might be circumstantial, strong evidence of nuclear signature. And also the anomalous heat effect is mostly produced under the gas desorption mode. Okay. And so the gas consumption rate is very small, very much small. And many appendix data you have seen from ResearchGate. Many details we have there. Thank you very much.
Thank you. reaction products, has there been an attempt to measure the gas reaction products from this reaction?
Yes, we need to measure, but we have not yet done that. As a major product, we expect the helium-4 in the case of deuterium gas, and helium-3 and deuterium, but the deuterium is very difficult to observe, so the helium-3. Another difficulty for mass spectrometry, however, we are expecting to do in future. And for transmutation, we need another analysis, of course.
Thank you very much for your interesting presentation. I have a question about neutron emission. You clearly said that some neutron emission is observed, although very, very small. Yes. And at what, from this experiment result, at what power increase point this neutron emission becomes dangerous? What is your estimation?
Yes, this level is still comparable to the background neutron level, very, very small. However, so if we make a power plant with this and making a more than 1 megawatt power, maybe we have a neutron emission comparable to the neutron standard source for experiment, you mean? I mean, so not very strong, I mean. We can protect very easily, very, very weak level, even with 1 megawatt power. Not dangerous for human beings. However, we need a shielding, of course, for the mental, safety. Mental, not biological, I think.
When you change the gas from hydrogen to deuterium, do you have some times where you have almost nothing or immediately start?
Right. In this case, for the copper nickel sample, we used only ordinary hydrogen gas. That means the light hydrogen gas. And for palladium-contained one, we use the deuterium because of our transition. However, we need to test with light hydrogen for palladium-contained sample too. However, up to now, we have no time to do that. We need to do that.
You mentioned a shell structure at the beginning of your presentation that you observed, and I'm interested in knowing a little bit more about that.
You mean the sample structure? Shell?
I wasn't clear. You mentioned that you observed a shell structure?
Shell structure of sample, you mean?
Yeah, SHELL.
Yes, just a moment. At the beginning, we have done some measurement using STEM EDS,
Yes.
in nanometer scale analysis. And we found this sample make a kind of nano island inside zirconia very homogeneous flake. That works, and maybe at the surface of nano island, we have reaction sites made.
Thank you.
You've got this turbulence thing going on. Would it be possible to have an air stirrer inside the chamber in order to?
Stirring air. That if we can put in some stirrer inside, that is possible, but maybe difficult because we have a gas vacuum sealing, and how we can make a stirrer inside the reaction chamber. And if we have a good idea, we can try. Using a magnetic stirrer, still we have problem. Of course, the sample itself is ferromagnetic, so, CNG, PNG sample is ferromagnetic, very strong. So by using a magnet, maybe we can make something, but that's the future, improvement. Interesting. But
Yes, please. What is the internal diameter of the cell?
diameter of what?
Internal diameter of this cell.
Cell?
Yes.
This one?
How big is it?
This is about It's 20 centimeter in height and 5 centimeter in diameter, something like that. Something like this.
Okay. Thank you very much again.